Dear students, I welcome you for the today's lecture related to the radiation in the subject of heat transfer. First, we will try to understand what is radiation, then what are the different common terms used in radiation, and lastly, the different laws of radiation, and then the numericals related to radiation. Now, the heat transfer that is there, in which we are having the three different modes of heat transfer, that is the conduction, convection, and radiation. In case of conduction, the energy is transferred by the adjacent molecular collisions inside the material. This inside the material terminology is very important. The energy is transferred by adjacent molecular collisions inside the material. The medium itself does not move. Medium doesn't move in this case, but it is taking place inside the material. However, in case of a convection, it is a process by which the heat energy is transferred by actual mass motion of heated fluid. Actual physical movement of a liquid is there in case of a convection. And in a radiation is a process by which the heat energy is transferred by electromagnetic waves in terms of the photons. So electromagnetic waves in terms of the photons, the energy is transferred. The body itself transmits the energy. So one by one, we will see the same example, that is the burning fire. And we are putting a rod, metal rod, and that metal rod is heated by conduction. In the upper surface, because the fluid or the air is getting heated, you feel the hot air. And third is by the radiation, the burning flame that gives you the radiation, and one can feel these radiations. So heat transfer is occurring because of this. Then the transfer of thermal energy by wave moving through the space. Then all objects radiate the energy. All objects, not only few ones, but all objects radiate the energy. You feel the radiation of thermal energy from sun, from bonfire, and from heated lamp or lighting bulb. So all these are our different examples which we can observe visually. Even though the all objects radiate energy, but the transmitted energy or the observed energy, that again is a function of a temperature. All objects which are above 0 degrees Celsius, 0 degrees Kelvin, all objects which are above 0 degree Kelvin, they are going to radiate. So it's a function of a temperature, and it is all talked in terms of a Kelvin. Heat by radiation is also known as infrared radiation. Now, how we are getting the energy from the sun, and that is the most abundant source of energy, but still not trapped to that extent. Nowadays, it is being trapped or utilized by using the photovoltaic cells and directly your solar pumps and solar water heaters and the different sources. These there are no particles between the sun and the earth. It is all vacuum, and so it cannot travel by conduction or convection, because for conduction you require a medium, you require a inside surface of the solid. For convection you require a medium. But so this energy transferred from sun to the earth is neither by conduction nor by convection. So there is a third source of energy, that is the radiation. And this radiation does not require the matter to transfer the thermal energy. All the sun energy that reaches the earth travels through the millions of kilometers through the empty space. And this is the electromagnetic radiations that is being transferred in the form of photons. So you can see this plate that is there. One plate is cold and one plate is hot. So hot plate that also transmits the thermal radiation and receives the thermal radiation. Then coming to the definitions of radiation. The transfer of energy across a system boundary. So system boundary is there, and it's the exchange of energy between the system boundary and the surrounding by means of an electromagnetic mechanism. So electromagnetic mechanism is the most important terminology, which is caused solely by the temperature difference. Radiations which gives off by a body because of its temperature is called the thermal radiation, and that is why it's a radiation energy or radiation it is talked. The thermal energy that is transferred directly from the source to the object in the form of electromagnetic rays or waves or photons. It can be in the form of rays, it can be in the form of waves, or it can be photons. The energy emitted by the matter in the form of electromagnetic waves as a result of change in electronic configurations of the atoms or molecules. This thermal radiation is restricted to a limited range of electromagnetic spectrum also. There are certain limitations for that. The electromagnetic energy is a type of energy that is radiated by the sun in the form of transverse waves vibrating at a right angle to the direction of the movement. Now there are different regions, that is your gamma ray region, X-ray region, ultraviolet region. Then it comes the thermal radiation and microwave radiation. It all depends on the frequency. In this thermal radiation, there is an infrared radiation as well as the visible region. We can see only this visible region, and we are not able to understand this infrared region. So heat can move by traveling an infrared wave, and these are the electromagnetic waves like light waves but with a longer wavelength. So this means that the infrared waves acts like a light waves. So they can travel through the vacuum. They travel at a very high speed as equivalent to that of the light. They can be reflected. They cannot travel through opaque objects. So energy transfer by radiation occurs at a speed of light and suffers no attenuation in vacuum. Then the radiation can also occur between the two bodies separated by a medium colder than the other bodies. Then these are the different properties, that is radiation heat transfer does not require any particles. Only way the energy can be transferred across the empty space. Radiation does not require the matter to transfer the thermal energy. So matter is not required. All matters can radiate energy. Matter is not required for the transfer of energy. Matter move नहीं हो रहा है. All matters can radiate energy. That depends on the temperature. All objects that are hotter than their surrounding, means a object and its surrounding, depending on that temperature difference, the amount of energy radiated is going to vary. Then there is no touching of the object. You can feel the thermal energy without touching it. Thermal energy, we can see the radiations. If we go close to the burning objects, we can feel the radiations there. In fact, the heat transfer by radiation is faster and it suffers no attenuation in vacuum. This is how the energy of the sun reaches the earth. The heat transfer studies, we are interested in thermal radiation, which is in the form of radiations emitted by the body because of their temperature difference. Now it is very important, all bodies at a temperature above absolute zero emit thermal radiations. Absolute zero, that is 0 degrees 0 Kelvin, emits thermal radiation. It is all the difference between the surrounding and the body temperature. Radiation is a volumetric phenomena and all solids, liquid and gases emit, absorb or transmit radiations to varying degrees. However, it is considered to be the surface phenomena for solids. Now, in case of conduction, the temperature heat transfer because of the conduction, it is the temperature difference that exists. It is directly proportional to temperature difference. Also, in case of convection, it is dependent on the temperature difference. However, in case of a radiation, it depends on the fourth power of the temperature difference. Fourth power of the temperature difference. So when no medium is present, radiation is the only mode of heat transfer. If there is no medium in earth, outside the earth, that means in space, there is no medium, it's a vacuum. But the energy is transferred. So radiations or the waves that can be transmitted. So this radiation differs from conduction and convection heat transfer mechanism in the sense that it does not require the presence of a material or medium to occur. Now the radiation, thermal radiation is a electromagnetic waves produced by the object because of their temperature. That means it depends on a temperature. So the amount of the radiation generated and the temperature as a function. As I'm going to increase the temperature, so the amount of radiation generated that also increases drastically. All objects emit radiations, but hot objects emit more radiation than the cold objects. So higher the temperature of an object, the more thermal radiation it gives off. Now when we do not see the thermal radiation because it occurs at the infrared wavelength visible to the human eye. So objects glow different colors at the different temperatures. So depending on the temperatures, you will get the different temperature colors. Now it is the graph that is showing at a 20 degrees Celsius relative power and the wavelength at 20 degrees Celsius and at a 600 degrees Celsius. This is the infrared region and this is the visible region. So the curve of 20 degrees Celsius does not extend into the visible region, and that is why we are not able to observe. This is the this is the curve at 20 degrees Celsius, right? And visible region is only this one. So as we increase the temperature, and as a result, this 600 degrees Celsius stove flame that is observed, and we can see it in a visible region. So it is all depending on the temperature. As you go below this, you will get such other curves like this. So that goes into the infrared region. So as the objects heat up, they start to give off the visible light or glow. And that is why we say that only higher temperatures we can observe. The rest of the other, they are in the infrared region. Then as the temperature rises, thermal radiation produces the shorter wavelength and higher energy light. We are able to see only the higher energy lights. At 100,000 degrees Celsius, the color is yellow orange, turning it to the white at 1500 degrees Celsius, and still the increase in the whiteness with the increase in temperature that can be observed. Now the black body spectrum. This is our visible light region, infrared region, ultraviolet light region. So the graph of the power versus the wavelength for a perfect black body is called the black body spectrum. The perfect black body is a surface that reflects nothing and emits pure thermal radiation. That reflects nothing, there is no reflection, and emits pure thermal radiation only. The white hot filament of a bulb is a good black body because all the light from the filament is the thermal radiation, and almost none of it is reflected from the other sources. The curve for 2600 degrees Celsius shows the radiation is emitted over the whole range of visible light. 2500 degrees Celsius, 600 degrees Celsius, 5500 degrees Celsius, it shows the complete range of visible light. Now the stars. The Sirius is the hot young star about twice as big as the sun and 22 times as bright as that of the sun. So these stars, they are also producing the different wavelengths. The distribution of energy between the different wavelengths depends strongly on the temperature. Because its temperature is hotter, Sirius appears bluer than the sun. That means sun we observe in the yellow, but if you will observe the Sirius, it becomes a blue because of the higher temperature. Then what happens to a radiant energy? The incident ray that is falling on a certain plate Some of it is reflected, some of it is transmitted, and some of it is absorbed. Alpha, that is the absorbed, then reflected, that is the R, and transmitted, that is the tau. So whatever the amount that is incident, that will be either absorbed, reflected, or transmitted. So 1, it's the summation, that will be equals to the 1. The total power emitted as a thermal radiation by a black body depends on the temperature T and the surface area A. The real surface, एक मिनट में है तो So the total power emitted as thermal radiations by a black body depends on the temperature and the surface area. The real surfaces usually emit less than the black body, typically between 10% to 90%. That depends on the properties of that. And the Kelvin temperature scale is used in the Stefan-Boltzmann formula because the thermal radiation depends on the temperature above absolute zero, that is 0 Kelvin. And that is why Stefan-Boltzmann formula and all other radiations calculation that has to be converted into the Kelvin. So when the thermal radiation strikes the body, it can be absorbed by the body, reflected from the body, or transmitted through a body. The absorptivity, the fraction of the incident radiation which is absorbed by the body. The reflectivity is a fraction of incident radiation which is reflected by the surface or the body. And the transmittivity is the fraction of incident radiation which are transmitted through the surface. So the sum of these fractions, that will be equals to 1. And then the radiation energy incident on the surface per unit area per unit time is called the irradiation G, and it's a function of the addition of absorptivity, reflectivity, and transmittivity. Now, since the color black is associated with a nearly complete absorption black body, that is, this is a lamp black coated, so the rise in the temperature is faster in this lamp black coated block as compared to the silver coated black block. So material that is a good absorber like lamp black is also a good emitter, and a material that is poor absorber like polished silver is also a poor emitter. Those which are good absorbers, they are only good emitters. Then objects tends to absorb the electromagnetic waves from their surroundings. An ideal absorber is called a black body, and an ideal reflector is called a white body. So absorber, it's a black body, and reflectors, they are the white body. The object tends to radiate, reflect the electromagnetic waves as efficiently as they can absorb them. Then the transfer of energy through the emission of the electromagnetic waves is called the radiation. So this is the rate of radiation, is the energy transmitted per unit area per unit time. That is what the energy transmitted joules per unit area per unit time, joules per meter square second, or you can write it in terms of watts per meter square. Now there are the two surfaces, and from one surface it is the Q1, the heat that is transmitted, radiated, and from the surface 2, which is at a temperature 2, the Q2 amount of the heat that is radiated. So heat flow per unit time that is nothing but watt per meter square, and which is nothing but a flux. Then the rate equation, the heat transfer by the electromagnetic waves or the photons, that is the emissive power of a surface, which is emissivity into the Stefan Boltzmann constant into the temperature raised to the fourth power of heat. So this plate, which is at a surface temperature Ts and having the area A, it radiates the Q amount of the heat, and also by convection it the heat is getting transferred. So when it's heat transfer by radiation, it becomes sigma epsilon Ts raised to 4 minus Ts raised T surrounding raised to the 4. That is the exchange of heat energy from the surface to the surrounding. So when the surface is completely enclosed by a certain uh, surface at a temperature T, which is the surrounding temperature, surrounding surface at a temperature T surrounding, the this plate that is reflecting the radiating the energy. So the net rate of radiation heat transfer between these two surfaces, that is given as Q radiation, which is equal to the emissivity into the Stefan Boltzmann constant into the area A, surface area A, and the temperature difference raised to the power 4. Where emissivity, a measure of how closely a surface approximates a black body, for which emissivity equal to 1 of the surface, and the Stefan Boltzmann constant having the value of 5.67 into 10 to the power minus 8 watt per meter square Kelvin raised to 4. The net radiation heat transfer, the difference between the rates of radiation emitted by the surface and the radiation absorbed. And this determination of the net rate of the transfer by radiation between the two surfaces is the complicated matter, since it depends on the properties of the surface, their orientation relative to each other, and the interaction of the medium between the surface with the radiation. And the radiation is usually significant relative to the conduction or natural convection, but negligible relative to the forced convection. Now, when the radiation and convection occurs simultaneously, then that is between a surface and a gas. Gas is also there, means a plate is there and the surrounding atmosphere is there. If it is a surrounding atmosphere, then with the plate as well as the surrounding air, from the plate you will get the radiations, and as there is surrounding or the air that is available, so by convection also the heat transfer will be there. So it's a combined heat transfer, that is because of the convection and because of the radiation. When it's a convection, then HA delta T is there, and if it's a radiation, then it's a epsilon sigma as into T s raised to the 4 minus Ts raised to the T surrounding raised to the 4. So Q total, that will be the combination of H combined, and where H combined, that incorporates the H convection plus H by radiation, and H convection will be as it is, and H radiation, that will be accommodating this Ts raised to 4 term, Ts minus T surrounding, and this epsilon and the sigma terms. all are there in terms of a H radiation, heat transfer coefficient, because of the radiation. Now, in case of a simultaneous heat transfer mechanism, almost there are three mechanisms of the heat transfer. A medium may involve only two of them simultaneously. Involves only two of them simultaneously. That is very important. Now, if we consider a solid which is opaque, the heat transfer in that solid is only by conduction and radiation in case of a semi-transparent solid. A solid may involve conduction or radiation, but not convection. Inside that, outside it can be convection, but inside it is only the conduction that will be there. A solid may involve convection and or radiation on its surface. सरफेस पे कन्वेक्शन से भी होगा एज वेल एज रेडिएशन से भी होगा हीट ट्रांसफर. Surface exposed to a fluid or the other surfaces, then the heat transfer is by conduction and possibly by radiation in a still fluid. In the absence of radiation, the heat transfer through a fluid is either by conduction or by convection. Absence of a radiation, it can be either conduction or convection, depending on the presence of any bulk fluid and motion. So generally it is the only two phenomena that is observed simultaneously. Most gases between the two solid surfaces do not interfere with the radiation. Liquids are usually strong absorbers of radiation. So in case of a conduction, it is the direct contact of the particles, that is your solid, liquid and gases, and solids are good conductor, gases are poor conductors. In case of convection, it is the transfer of energy by the bulk movement of the matter, that is your fluid. Then currents, wind or water currents, hot air balloons for example. Then in case of a radiation, the transfer of energy by the waves, electromagnetic waves. Only radiant energy that is absorbed becomes the thermal energy. Shiny or the light color reflect, dull and the dark colors they get absorbed. So black body, that is the idealized surface that emits radiations at the maximum rate. And for black body, the emissivity equals to the 1. The perfect black body, the emissivity that is considered to be as the 1. Black body radiation represents the maximum amount of radiation that can be emitted from a surface at a specified temperature. Again, it's a function of a temperature. Then absorptivity alpha, the fraction of radiation energy incident on the surface that is absorbed. So black body is a model of perfect radiator. It absorbs all the energy that reaches it, reflects nothing. Therefore, the energy emitted by a black body is the theoretically maximum energy, that is Q, which is considered to be equal to the sigma into T raised to 4, where emissivity equals to the 1. So this is the Stefan-Boltzmann law, and the wavelength at which the maximum amount of the heat that occurs. Then real bodies will emit less radiations than a black body. Here the emissivity, which is a number between 0 and 1, such a body would be called as a gray, because the emissivity is the average over the spectrum. So the radiations from a small body to its surroundings, both the body and its surroundings emit thermal radiations. The net heat transfer will be from the hotter to the colder body. The net heat transfer is then for the smaller temperature difference in terms of the T wall and raised to the 4 minus T infinity or T surrounding raised to the 4. Black body is a perfect emitter. In a black body enclosure, radiation is the isotropic. Black body is a perfect emitter in each direction. Black body is a perfect emitter at any wavelength, and the total radiation of a black body into vacuum is a function of temperature only. So this, if the material is opaque, then alpha plus rho equals to the 1, where alpha is your absorptivity and rho is your reflectivity. Transmittivity is not there for the opaque objects. Now coming to a gray body. When the surface absorbs some fixed percentage of incident radiation, absorption is there into a certain fixed percentage of the incident radiation. The absorptivity of a surface does not vary with the temperature and the wavelength of the incident thermal radiation. So this absorptivity is not a function of a temperature and the wavelength of the incident radiation. This gray body does not exist in real terms. It's a theoretical term. When the surface absorbs some fixed percentage of incident radiation, then there is a transparent body, the surface or a body which allows all the thermal radiations to pass through it. It allows all the thermal radiation to pass through it. So transmittivity equals to the 1. If the transmittivity equals to the 1, our equation will be incorporating absorptivity and reflectivity, that will become 0. So glass transmits maximum thermal radiations received from the sun, but it absorbs almost all radiations at lower temperature radiations when it's a lower temperature. Transmittivity varies with the wavelength of the incident radiation. This transmittivity, it is a function of a wavelength, but the gray body is not a function of a wavelength. Then opaque body, it does not transmit any thermal radiation falling on it. It does not transmit any thermal radiations falling on it. Does not transmit, that means the transmittivity is 0. That is the absorptivity plus reflectivity equals to the 1. So maximum of the engineering bodies are opaque. So transparent body and opaque body, it's a opposite. Opaque body does not transmit, and transparent body, it transmits completely. Then a white body, a body reflects all the incident radiation falling on it. So reflectivity equals to 1. First we have talked about transmittivity. Now we are talking about the reflectivity. So body reflects all the incident radiations falling on it. It is the reflectivity is 1. So if the reflection of radiations is uniform or regular, it is called as specular body. Highly polished or smooth surface refraction is regular or uniform, it is called a specular body. And if the reflection of radiation is diffused, it is called the absolute diffused body. Then radiosity, it indicates the radiations leaving the surface per unit time per unit area. The difference between the emissive power and radiosity is that the latter includes reflected energy also in addition to the original emission.